Okay, so now I'm going to show you how to implement the batching technique. So we always recommend that users who are planning on bulk downloads to work with the batching technique so that you can get your products as efficiently as possible without running into any breakage or any server timeouts. So for this example, we are going to work with this mega program for the SMAX 0723, the JWST deep field. This is an ERO program, and I'm going to be getting observations for nearest for this program. So let's go ahead and do our call. I'm going to use query criteria so I can work with a bunch of different parameters that identify the observations. So the program is called 2736. So if you remember from the cells before, the metadata is proposal ID 2736. We want to work with nearest data. So the metadata is called instrument name, and I'm going to specify nearest. I want to work with only spectral data. So I'm going to set data product type. This is a new metadata, and I'm going to set it to spectrum. And just for good measure, I'm going to specify that this JWST data. It is a redundant thing to do because nearest is JWST, but I think there are some studies being undergone, I think by Thomas and Dick, to see if specifying obs collection will minimize the query speed or maximize the query speed. So this is my query, and I'm going to assign a new variable called n_obs to just to the length of the table. In other words, the number of results that we get. Okay, so this is a pretty hefty program. So we have just under 2,000 individual observations for this query. Let's just play around with the first 20 observations. So let's shrink this a little bit and reassign obs table to just the first 20 rows of the previous obs table. And this is where we begin our batching method. So I'm going to assign the batch size to 5, and let's go ahead and create the batches. So I'm assigning obs batches to what I'm about to do. So I'm indexing obs table from index to in steps of 5 for index in range 0 to the entire length of the table and in steps of 5. And let's go ahead and print that out and make sure that we're working with the right set of batches. This looks good. So we had 20 observations, and now we have 4 groups of 5 observations. So basically what we're going to be doing now is iterating through each group so that instead of getting all the products for all 20 observations at once, we get the products for the first batch, then the second batch, and so on. So this is our iterating cell. So I'm just doing a quick for loop for index batch in obs batches. This is my progress indicator. And now I'm going to be getting the obs IDs. So that is a metadata, so I would just index it like any other column, and then I'm going to print the obs IDs just as a progress indicator. And now I'm going to get the products from these obs IDs. So in the previous example, I showed you how to get the products from a single row of an observations table, but you can work with multiple observations by feeding it the list of obs IDs or by feeding it an entire table. Either way works fine. So I'm going to assign products to the output of get product list. I'm going to feed obs IDs, and I don't want all the products for every single observation. So I'm going to do some filtering to minimize the load of our server even further. I only want to get the science products for this program, and I only want to get calibration level 3 products. So let me introduce you to another method called filter products. and it looks like this. You feed it the products that you want to filter and then the metadata that you want to filter by. So in this case, I only want science products, so I'm going to set the product type metadata to science and the calibration level metadata to 3. And now I'm going to print the file names of these filtered products just to show you what it looks like. So we're iterating in batches. We get 15 products per batch, it looks like. So instead of getting all 60 products at once, you're getting 15 products at a time. And that is basically the whole purpose of the batching method, is you're splitting up your query into multiple little queries so that the system doesn't get overloaded. And I'm not going to be downloading the files in real time, but if I did want to download the files, the call would look something like this. So observations.download products, and then you just feed it the filtered products. Keep in mind, if you do try to download on your own version of this notebook, the downloads will not be on your local computer. They're going to be downloaded in the Jupyter Lab instance. All right, let's jump right in. So typically for most of your queries, you'll be fine just working with astroquery.mast.observations. So observations, working with the main database and working with those criteria should be enough for your specific case. But if you want a more advanced query, you can work with a class called MAST. And that MAST class will basically give you access to specific databases for the particular query that you're trying to make. So, for example, if you are a user who's trying to make an SI keyword search or science instrument keyword search for, let's say, nearest source observations, so single object slitless spectroscopy observations, you can use MAST to directly access the nearest database, the filtered nearest database, rather than our main database. And that'll give you more control over the queries that you're trying to make, because the criteria that you'll be working with in this case is the header keywords that are part of the nearest data, the nearest files, rather than the metadata that you just saw with query criteria. Hopefully that makes sense. Because it is more Python heavy and it depends heavily on the syntax of the way that you format your parameters, I do have these two helper functions that are going to help me with the syntax of things. This is not built into MAST itself. It's just something that's been pre-written, but feel free to copy paste for future reference for your specific notebook needs and query needs. Okay, so let's say I'm an astronomer who wants to look up nearest source observations for commissioning data and early release science data, and I want to work with TSO data because it's source. Let's go ahead and set up our criteria, and the criteria has to be structured in a dictionary. So I'm going to set the category keyword to commissioning data and early release science data. I want the exposure type keyword for all of my query returns to be nearest source. And because this is a nearest source, I'm going to set time series observation visit to true. And last but not least, I'm going to add a time component to this query. So I only want observations taken between June 1st and August 4th of this year. So the time component to these queries comes in two flavors. You can have the regular ISO flavor, or you can feed it the MJD or modern Julian date flavor. So I'm going to be working with the MJD version just for the sake of this notebook. So day obs is the actual keyword that would be found in like the primary header keyword of your FITS file. But because I'm working with MJD, I just add the extra underscore MJD to it. And I'm going to set the time frame. So I'm going to use my helper function set underscore MJD underscore range. Set underscore MJD underscore range. And I want observations between August 1st and, June 1st and August 4th. Okay, and this is closed. Okay, so now I'm going to restructure, this is the element that's a little confusing. I'm going to restructure this keywords dictionary into the correct syntax for the database that I want to call from. So the nearest database is not going to understand what this is, but the format that is available for the nearest database is shown on this web page here. So the way I accessed it was just by clicking the little link here. All the links that are relevant to you are in the notebooks already. I just clicked the MAST JWST filtered nearest link, and that took me to a page that shows the list of all of the JWST specific databases that you can work with. So I'm working with nearest. The format of the parameters needs to be in the following way. So we have two keys that are the primary keys, so a columns key, and then the filters key. And then the keyword dictionary that I just made just now is going to go under filters because those are the filters that I'm working with. Let's go ahead and make a dictionary that looks like that. So columns. For the columns keyword value, I'm going to put the wildcard asterisk because I want all of the metadata returned to me in the table. And then the second key is called filters. And this is where I'm going to use my second helper function called setParams, and that's basically going to restructure my keywords dictionary into the correct syntax that will be understandable by the database in the backend. Forgot a parentheses here. Comma. Okay, so let's go ahead and see what that looks like. Okay, so yeah, the param structure looks like what you see in the documentation here. So columns, filters, and then param name and values for each key and keyword value pair. So now we have everything we need pretty much. So let's go ahead and make a call. So again, the database that I want to work with is called mast.jwst.filtered.nearest. And I'm going to go ahead and call the MAST class. I'm going to call the method called service request, which is going to be the bridge that communicates my query with the database. And I'm going to go ahead and feed it the service that I want to communicate with and the parameters that I want to filter by. Let's go ahead and take a look at what that notebook looks like. So yeah, here we have the file names, the ASN pool, a bunch of metadata that you did not see in the previous notebook, and that's because this metadata is the science instrument keywords. It's not the metadata that the main database goes by because we're accessing a different database. So exposure type is nearest source as we specified, and a bunch of other useful information. Okay, so now I have a little diagram that'll help me explain what we're going to do with this information. So what we just did was we used the MAST class, which is the sister of observations, and we use it to access data using a set of criteria, which are the SI keywords, to pull out products, final stage 3 products from, or rather observations from the nearest database. So now what we're going to do is we are going to take the file name science instrument keyword for these individual observations, and we're going to do some Python magic to convert it to a metadata called obs_id, which is separate from the obs ID that we worked with in the previous notebook. But it is a metadata that's understood by observations. So that from that point on, everything will become familiar to you again, because we're going to be working with observations again. And we're going to be using this metadata to query for individual observations and then download the products from there. The reason why we're doing this whole roundabout thing is because the results that we got from the nearest database are not observations, they're stage 3 products. So we want to make sure that we have access to all the observations that pertain to all the products for the given obs IDs. So let's go ahead and do that Python magic. So I'm going to extract the file names from the table above. So I'm going to do list set. So these are built-in functions in Python that are super helpful. You just have to commit them to memory. So set will create a set of unique keywords. So if there's any duplicates, it'll get rid of the duplicates. And then list just turns it into a list, which I can manipulate like a lot easier. So the table was called T. That's a variable I assigned it to. And the column that I want to filter by is file name. And then I'm going to really quickly just print the first index. So you have a better idea of what this is going to look like. So I'm basically going to do some Python magic to manipulate this string so that I only get everything highlighted. So the suffix x1d ins.bits and the extension will be removed. And all that will be left is the obs underscore ID, which is in the file name itself. That's why we're working with this. So let's go ahead and assign IDs to this iteration. So I'm going to iterate for every file. For file name and file names, I'm going to take file name, I'm going to split it by the underscore, and I'm going to get everything except for the suffix and the file extension, as I mentioned. And then I'm going to join everything again with the underscore. So let me just print that out really quick. And there we go. Now we have the obs underscore ID observational metadata derived from the file name itself. So let's go ahead and print all of them. Looks good. And let's go ahead and get the observations. So MAST observations, we're reuniting with our observations class. We're going to query based on criteria. And the criteria we're working with is obs underscore ID, which is what we just derived from the file names above. And then let's go ahead and take a look at what that looks like. So yeah, now we have the individual observations. There's the obs ID. You see the target name. Now this metadata probably looks familiar to you. It's basically the main database metadata that we worked with in the previous notebook. Let me go ahead and collapse this. And just a quick print statement. We got 14 observations from this query. Okay, so now we query for the data products. So we're going to do some batching again. This probably looks familiar to you. This time I'm going to set the batch size to 4. And I'm going to set batches by iterating through matched obs. We're going to index based on batch size for I in range 0 all the way to the end of matched obs in steps of 4. I have a typo here. Okay, let's take a look at batches and make sure that looks okay. So 4, 8, 12, 14. That's perfect. So we have 4 batches. Last batch is 2, has 2 observations because we're working with 14 now. Okay, so now let's get the products for these observations. So we're going to call observations.getProductList, and we called it batches. So we're going to iterate through batches and get the product list for each group of observations within the batches. So let's run that. And now let's go ahead and do a stack and a unique. So we're going to get rid of all the duplicates using unique, and I'm going to vstack the tables of products that we got from the previous result. And the key that we want to make this unique culling is with product file name. So if something has the same product file name, we just cull it. And that should be all we need. And these are our products that we can now download. So we have some minimum recommended products. The product file name is listed here. We have some association files, some uncalibrated files. So we're going to get rid of that. Let's go ahead and filter these products. So filtered products is equal to observations. This is starting to look familiar, hopefully. Observations.filter products. And I only want to get science and info files. So let's go ahead and do that. So product type is equal to science and info. And I only want level 2 and 3 products. So calibration level is equal to 2 and 3. And we only want spectral data. So because we're going to be plotting that later. So data product type is equal to spectrum. I should add a little caveat here. So the best way to filter for spectral data is to work based directly off of the science instrument keywords. When you work with the main database criteria by setting data product type equal to spectrum, that's not always going to give you only spectral science data. It might get you like JPEGs and things like that, and data that will help you understand the spectra, but not necessarily the spectra always. So that's just a heads up if you end up getting non-spectral data from this query, that's why. Okay, so, whoops. So yeah, when you filter products, you need to give it the products that you want to filter. Products. And let's go ahead and take a look. And these are our final products. So this is the data URI. Let's go ahead and just filter for a couple single columns. Let's look at size, let's look at calibration level, let's look at instrument name. No instrument name. I guess that's only observations. Okay, so this is what it looks like. So we have stage 2 and 3 data products. We have some association files. It shows you the size, the given size in bytes, and everything looks good. So now let's go ahead and do some plotting. But before I do that, if you are working with proprietary data, you are going to have to create a token with your MAST account information to access that data through AstroQuery MAST, the same way that it would prompt you with your MAST account information on the actual portal UI. So that looks a little like this. The link again is available in the Jupyter notebook. You can go to auth.mast, click on tokens, and then you have a key that you can use here. You can also create a brand new one by clicking the create token button and just calling it my token or whatever you want. And that is the token that you can work with. And to log into the UI or the API, you would just call the observations.login method as seen right here. And now we're going to download the products really quick. So this is a flag that you can set to true, which will basically automatically download a bash script to your local directory, your current working directory, which you can then use to download the products one by one instead of downloading it directly. But let me just go ahead and download the products directly myself. And let's do some plotting. And here we have some spectral data with nearest saw. So you see the first and second orders. And that is how you do queries with the science instrument keywords using the MAST class.